B Part 8, Miscellaneous Tips on Applied Math and Physics. Today is September 3rd, 2025. So, Lecture 9, Hodge Operator and Wedge Product. 1. Item 1. Definition of wedge product, this case. Let V be a vector space. The wedge product is a bilinear, in this case, unsymmetric operation. You see, there's a U wedge V is defined using the tensor product, okay? You can see here, by definition, that this wedge product is bilinear. You see, you can swap U and V, then you obtain minus over here. You see, this is by definition. And also, the wedge U will be 0. See, by definition. You see. Now we introduce the Hodge dual. Okay, well, Hodge dual is a map that take a wedge product of k vectors and returns an n minus k form. You see, that's by definition. Okay. Now, formally, you see this asterisk. This is a map. Okay. This is a k vectors. This n minus k forms. Okay. By definition. Okay. These maps from here to there. Remark: Hodge dual and wedge product mimic the cross product in R3. See, that's a very important, because you see, I'll talk this later on this lecture. The Hodge dual maps by vectors, okay? This belongs to this space here, to a vector. See, this number 2 here, this number 1 over there is just k and n minus k. You see, in this case, n is 3, okay, and k in this case is 2. So this is from 2 to 1. Okay, that's the 2 vectors, and this is one form. Apply this operator, for instance, E1, wedge U2, this will be E3. Attention now, E3 is contravariant base vectors, which belong to the dual space. Likewise, okay, the base is E2, wedge E3, okay. This leads to E1. Again, E1 is one of the basis vectors. In this case, I'll call it a covector, okay? And this belongs to the dual or this cotangent space, for instance. Likewise, E3, wedge U1 is U2. You see, you can hear, okay, this is cyclic. After 1 comes 2. After 2 comes 3. After 3 comes 1. Likewise, this over here, you see, in this case is 2 here, and this, the next is 3. 3 here, the next is 1. And this E1, the next is E2. It's quite easy when you apply the cyclic, called the permutation. See? Recall that in Cartesian coordinates, okay, E1, you see, the covariant and contravariant, they coincide, okay, in Cartesian coordinates. So this E1 is identical to E1 over here, and so on. Now, it's a very, very important here. From here, I jump to there. Consider the figure where the green S, okay, is the area, okay, and S is given by, you see, these seams, okay, mimic the cross product. That's for you to understand. So this is dx2 while dx3. Now apply to uv. This x3, dx1, apply to uv, and this is dx1 wedge dx2. You see the analogous, okay, how it mimics, okay? This behaves, that's a very interesting. is analogous to the unity vector k. You see, that's interesting. You see, this here is analogous to k over here, the unity vector, okay, that the x3 direction. This one is I, and this one is j. You see clearly, okay, that dx1 divided dx2, you see it's analogous to the cross product, okay? You just rotate x1 and give k. Likewise, x1, x3, the x3, x1, you just rotate and j, okay, which will be analogous to E2. This case, the last one, okay, j cross k is I. It's just, you see, 2 here correspond to j, 3 correspond to k. Again, 3k, and this case I is 1, okay, the unit vector in R3. What is important just for you to understand, you see, here the area S, you see, if you develop this will come to the area S on green one. And also, this case, this example, I project the green, or this is the pumpkin color, okay? So this I call S3. S3 is perpendicular to the plane x1 and x2. You see, you just obtain this using the determinant, okay? So x3 is project area in x1, x2. I could show the other two projections, okay, on this x1, x2, and on the plane x2 and x3. But in this example, this is a particular case. I just project the green one on the pumpkin, okay, color here, x1 and x2, which can be represented by a determinant, okay? Now, the volume is given by, you see this volume V here, okay, is dxi, y dxj, y dxk. Applied to u, v, and w, here I have to apply to 3 vectors, okay? This here leads to the determinant 3 by 3. This I use in classical mechanics, you see, in R3, in this case, area and volume in classical mechanics mimic the intrinsic geometry, in which can be extended to higher dimension. This is a very, very, very important issue in intrinsic geometry, because if I use this determinant, I can extend, okay, the analogous to the cross product. I can extend for a determinant to be 4 by 4 and so on. I can work in the higher dimension spaces, okay? Now in classical mechanics, okay, the cross product is only applied to R3, okay? That's a very, very important, okay? In R4, you never use, you don't get this over here unless you use a determinant 4 by 4, okay? That's a limit for R3, is a determinant 3 by 3. That's clear what I'm saying, because we are dealing with the intrinsic geometry, okay, to represent, okay, the wedge product, this here giving another one, for instance, dxi, dxj, dxk, and dxm, for instance, okay? In the 4th dimension, I use analogous determinant over there, okay? Just to mimic what we have on 3 dimension. That's a very, very important issue when you will be dealing with, this case, theory of relativity. Okay, that's it. That's important.